buterevu oli ku BBS telefine yaffe ey'obwakabaka bwa Buganda. Olunaku lw'eggulo twatandise enteekateeka eno ey'okuba nti tukwongerayo mu maaso n'okwongera okusomesa ebintu eby'enjawulo bannaffe aba Maryland ne bagamba nti nabo abaagala okwongera okutegeeza abantu nti ddala gye bali era basomesa abaana naddala okuva ku sini ey'osooka paka ku sini ey'omukaaga. Kale bana abali mu lummula naye abazadde mujjukire nti essomero eryo essomero ddungi era lisobola ddala okusomesa omwana wo n'abeera ddala nga asoma bulungi. Olunaku olwaleero tuzzeemu nate nti jo Mr. Lutaaya yasomesezza ku HIT kale olunaku olwaleero era recap netugamba tusooke abaatandika nayo era yebadde egenda mu maaso. Ku ssaawa eno azze butereevu okwongereza wali we yakomye era nga bw'ogenda maaso n'okuba nti otunudde ebintu abasuze okuba nga tulusoma jjo ne bye yasembezaayo nga bibaddeko ebiri kale butereevu twagala ayongerezaawo atwalire ddala mu maaso. Mr. Lutaaya Kenneth ava ku Namugongo Uganda Matters SS era butereevu njagala Mr. Lutaaya abantu babadde baddamu kali asoose ak'eggulo obaddemu ezo ennamba z'obadde ogezaako okubalabala ebitali byangu nnyo eri abantu abamu abantu baabo bali mu kirasi twagala ogende mu maaso nabo.
Good morning, our dear viewers, and once again, good morning to the candidates. As we know, in our profession, it is a tradition to always review the previous lesson, and what you've been watching from yesterday was basically a follow-up on the right protocol. However, today I would like to pick it up from where we left it yesterday, where we're trying to do simple calculations on how we can determine the quantity of heat required to raise the temperature of any given mass of a substance. So yesterday I tried to do two examples. Both of them were unique in a certain way, as you have seen. I did an example where the mass was given in kilograms and specific capacity is in reference to a 1 kilogram mass of the substance. Then I also did an example where the mass was given in grams, and it required us to first of all make the conversion from grams to kilograms in order for us to compute the heat in joules, given a specific capacity in reference to a 1 kilogram mass. So I would like to do one more example for you, my dear candidates out there, just to strengthen on the ways in which these questions can be set. This will be my last example on this, after which I'll then move on describing experiments, something which, if we're in the lab, we would do practically here, but given the limited airtime that we have for the program, I was not in position to prepare the apparatus to show you how we can demonstrate this. But I know that when we go back, the teachers will probably try and go through it. So my last example is going to be one which the examiner may set for us, and this time probably he's not asking us to find the quantity of heat involved, but rather he gives us the quantity of heat involved and maybe asks us a question on what could be the specific capacity of the substance that is requiring this heat in order to cause a certain temperature change. So if you're out there and you're following me, allow me read to you this example, and then later on we shall try and go through it, all of us. So my example, I must quote, I've picked a particular question from the question bank, those little books which are already printed by UNEB, having the past papers. I picked this question from a paper which was set in 2000, in the year 2000, UCE 535/1, that is paper 1. And it reads that when a block of iron of mass 2 kilograms, when a block of iron of mass 2 kilograms absorbs 19 kilojoules of heat, when a block of iron of mass 2 kilograms absorbs 19 kilojoules of heat, At this moment, I must apologize for viewers out there who are trying to enjoy the program, but probably, yeah, you don't know what we are talking about. When I mention 19 kilojoules, I can imagine what is going through your head, but I'm quite certain that the candidate out there must be following and knows what I'm understanding. If you're next to one, you can look at what they're writing down, then you'll understand. So we're saying a block of iron of mass 2 kilograms absorbs 19 kilojoules of heat, comma, its temperature rises by 10 degrees Celsius, full stop. Its temperature rises by 10 degrees Celsius, full stop. Find the specific capacity of the piece of iron. Find the specific capacity of this piece of iron. Find the specific capacity of this piece of iron. So like yesterday, and indeed it is always my tradition to always summarize the question. That's a good way of presenting your work, even to you candidates out there. After reading through the question, it's always good that you summarize it. I want to summarize this by saying that I'm presented with a mass. I'm presented with a mass of iron equivalent to 2 kilograms. And they're telling me that the heat it absorbs is 19 kilojoules. When it absorbs this heat, the question is mentioning that it will gain a temperature rise of 10 degrees C. So yesterday I talked about the term delta theta. And we said that this is the change in the temperature acquired by the body after absorbing heat. This change may be a rise, and indeed it may also be a drop in the temperature. So for this case, the question is clear, stating that there was a rise in the temperature, but it brought about a change in the temperature of 10 degrees C. So they're asking us this time that what is the specific capacity of the iron? This time we are looking for the specific capacity of the iron. So after summarizing my question, I am going to go on and use the equation which I talked about yesterday that we use in order to determine the quantity of heat. Why am I using this equation? This equation involves the mass, temperature change, and indeed it also involves the specific capacity. So using the equation that heat absorbed is mass times specific capacity times the temperature change, we are seeing that I know the value of the heat absorbed. It has been mentioned as 19 kilojoules. However, this equation gives me the heat in joules. Now, there is a trick also in this question, and like I mentioned yesterday, that's why I've picked out these 3 examples in order to give you a basis on which most of the questions that you come across in the question bank will be set. This one, I'm also incorporating 2 techniques. Number 1, I'm giving you a heat which is not directly in joules. Number 2, I'm giving you a temperature change, but rather not the temperatures from which the body was coming and to where it is going. And then I'm asking you to solve for the specific capacity. We are aware with our metric system, anything to do with kilo, that means it has been multiplied by 1,000. Or if we are moving from kilojoules, let me state it in this manner. If we are moving from kilojoules and then we want to go to joules, it means we have to multiply by 1,000. Which means that if I was coming from joules to kilojoules, then I must have divided by 1,000. So I'm going to go on and convert this to joules, which is the required unit for this equation to be valid. And 19 kilojoules, so 19 times 1,000, I think I'm going to go to 19,000 joules of energy. So it is this value that I'm going to come and substitute in this equation, but not this one, for the reason that I've just explained to you. This equation is valid if the heat energy that we're calculating is to be in the units of joules. What we have been given is a heat in kilojoules. So that's why I first of all made that conversion from kilojoules to joules. So on this side is the heat energy, which is 19,000. We are having a mass of 2 kilograms. Specific capacity, unknown. This is what we are looking for. But temperature difference is 10 degrees. Again, I'm going to apologize to the viewers out there who are not so much familiar with science but are interested in following us. There are a lot of things that we do in science, especially with the way in which we present our information. You're realizing that when I come on substituting some of these things, I don't bring along the units because they're not going to participate in the mathematics, but rather will only help me predict the unit, and then I'll bring them later on. So that's why I'm not putting here degrees Celsius, I'm not putting here the unit for kilogram. Again, I'm not putting here the joules because it's not participating in the mathematics. So I have 19,000 equals 20 C. I divide by 20 on both sides, and the mathematics gives us a solution to that, which we can get using the calculator. If you try and calculate this, probably you might land at 950 joules per kilogram per Kelvin, if my mathematics is correct. So, like I said, now the units can come back and appear. So, these are the 3 basic ways to you, my candidates out there, in which UNEB may test us on the concept of calculating heat. We can give you a direct question of just calculating the quantity of heat, or I may change a few units here and there, because, again, I want to see, did you understand that lesson of Form 1 where we're talking of SI units? And lastly, I may give you the heat and then ask you any of the other terms. So here, I've chosen to ask you about the specific heat capacity. But when you go and check in the question bank, which I strongly encourage and advise all of you to do, you're going to come across questions where they're asking you the mass given the specific capacity and the temperature difference plus the heat energy involved. Or you may come across questions where they're asking you to find the temperature change given the mass and specific capacity plus the heat energy involved. But because of time, I only picked out these 3 examples, which are enough to demonstrate, at least, and give you a basis to go on and then try and do the other related calculations from the question bank or any reference book of your choice. So this is it, and I hope that people out there pick a leaf from these 3 examples and go on and try out these things. Now, so far, I've talked about heat capacity, specific capacity, and its application in the calculation. And then I've also done the various ways in which the number can be set. But there is a statement which I made yesterday, and it is also showing up even in the calculations. We talked of the specific capacity of any substance being a constant value. So the question is, how do we know that the specific capacity of water is 4200 joules per kilograms per Kelvin? How do we know that the specific capacity may be of a substance made out of copper material is 400 joules per kilogram per Kelvin? I want to inform you, dear candidates, that as you all know, physics is a science, and in science we base on facts using experiments. So, how do we arrive at these values? We can go to the lab, follow a certain set of procedures, and then we shall indeed deduce that the specific capacity of water is that value. So at this point in time, allow me to talk about the various experiments which we can conduct in order for us to determine the values of these of the specific capacities for the various substances. My main focus is going to be on water and the solid substance. I'll use an example of copper, which is the common material from which most of the things that we use around us is made. So, experiments to determine the specific capacity of a liquid. Let me start with liquids, and I'm going to use water as my example. Excuse me. You will forgive me for my handwriting. The letters might look small, but I'm quite sure that my producer in the studio here is doing the best in trying to zoom in so that at least it's visible for you viewers out there. Now, before I go on and discuss the experiments, I must point out a few things. That the methods that we evoke when we are trying to determine the specific capacity of any substance are basically two. There is what we call the electrical method, and then there is also what we call the method of mixtures. At this level, I'm going to talk about only those two. Maybe if you go to the advanced level, we shall then even talk about other methods that are completely different from these two. But for this level, our syllabus dictates that we basically are equipped with the knowledge on those two. So, method one. I'm going to talk about the electrical method. If I wish to determine the specific capacity of a liquid, e.g. water, using the electrical method, what do I need? I'm going to use a calorimeter. A calorimeter being a metal can, usually made out of copper or aluminium or alloys involving one of those compounds. I am going to need a constant temperature bath. I am going to need a thermometer. I am going to need an electrical source. And in the lab, our electrical source is usually a battery. Because I need an electrical source, I need to monitor how much of this electrical energy am I going to supply. Which means that I need a voltmeter and an ammeter. As we're all aware, those of us who have done the topic of electricity, those are our measuring instruments in the lab for current and voltage. So, I want to present this in the best way and in the briefest way for all of you candidates out there. Number one, we are aware that when we are answering a question on describing an experiment in physics, then we don't need to write down the set of apparatus as much as I've talked about them, but we don't need to write them down. Why don't we need to write them down? At the end of the day, every physics experiment is accompanied with a diagram. And once we draw the diagram and clearly label it, then it means that you have also mentioned the apparatus that are involved. So I'm going to straight away go on my diagram. So what I'm doing here is drawing a very simple diagram to illustrate the setup of the apparatus if we wish to carry out this experiment. Yes. Of course, this is my battery. Physics definition of a battery, simply an arrangement of cells connected in series. This is my ammeter, this is my voltmeter. This is the heating element of my electrical heater. This is my liquid under test. Let me call it specimen liquid. But like I said, at this level, most of our experiments will be designed on the liquid, which is commonly used by us, that is water. This is my calorimeter. This is my thermometer. This is my stirrer. And then this is my constant temperature bath. These are usually insulating felt pads on which we place the calorimeter. I hope my diagram is very clear. May not be so much to detail, but like I said, during these lessons, I strongly advise that people who have the reference books pick them up and then look at what we're doing so that they can try and follow up. So this is my setup of the apparatus. Now, what am I going to do? What I'm going to do is going to come, I'm going to write it down below this apparatus. However, because of time, I may not write all the procedures, so I'm just going to talk about them. Then I'm going to also do the mathematics that is involved so that we arrive at the deduction that I'm looking for. So we go to the lab, pick up those apparatus, arrange them as shown in the figure that I've put on my board here. First things first, let me involve a switch since I'm going to, but some diagrams may not involve the switch. Oh, before I go any further, what is the purpose of labeling this diagram? I hope that one I've made it clear to all the candidates out there. It is because in physics, we may not write the procedures for the examiner that, like in some subjects, how they do it, that, the apparatus involved. But for us, what we do, we just draw our well-labeled diagram, and then it will communicate to the examiner that during this experiment, I'm going to need this, I'm going to need that, I'm going to need that, as shown on the diagram. So I'll close my switch. Before I close the switch, I want you viewers out there, especially the candidates, to listen to me carefully on this part because I don't want to use a lot of time while I'm trying to write down these procedures. First thing, after pouring my liquid in the calorimeter, I am going to measure the temperature of that liquid. And since the liquid is being poured into the calorimeter, then it means that under thermodynamic conditions, even the calorimeter will obtain the same temperature. What am I talking about? If we get cold water and pour it in a kettle. After some time, if you wish to know at what temperature the water is, you're going to come and you may not have direct contact with the water, but you can simply feel the kettle. And then it will give you a picture that, oh, the water is probably at this temperature. Why? Because when we obtain thermodynamic equilibrium, then the water and the kettle will be at the same temperature. So even here, after pouring the water there, give it some time, measure the initial reading of the thermometer. I'm going to record this as theta 1. Of course, it will be a certain temperature. I'm using the term theta 1 to refer to that temperature. Depending on the conditions under which you're going to carry out the experiment, can be any temperature. However, this will be the temperature of the liquid and the calorimeter in the initial stages of the experiment. That is before I go on and do the heating. So after that, I'll close my switch and then heat the liquid for a certain period of time. Of course, I'll start the stop clock as soon as I close the switch, and then the heating continues. After a certain time, you can heat for 5 minutes, 10 minutes, hours. The choice is yours, depending on what temperature what temperature change you're looking for. But in the lab setting, we shall not heat for so long. Maybe I can heat for around 5 minutes max, or 10, depending, but not for so long. During the heating, the heater is going to supply electrical energy to the liquid, and therefore the liquid will start gaining temperature. But because we say the liquid is in contact with the calorimeter, the fact that it's seated, we poured it in the calorimeter, it means that even the calorimeter will also start increasing in temperature. So, after my certain period of time, which I'm going to call T, after a certain period of time, comma T, we are saying that stop the heating by opening the switch. Quickly read the new quickly take the new reading of the thermometer. And we call it as theta 2. Oh, I forgot to mention something. After this time, when we've obtained a certain temperature rise, we shall first of all need to take the ammeter reading before I open the switch. Maybe it is reading a certain value I, and then also take the voltmeter reading. Maybe it's a certain value V. I'm using I and V to represent that ammeter reading and the voltmeter reading. So even after obtaining the new temperature, theta 2, we then go on and study what is the theory behind this experiment. And this is the theory behind the experiment. When the heating was going on, water is gaining energy, even the calorimeter is rising in temperature. Because we already know from that topic of energy, which we usually do in Form 2, that energy can neither be created nor lost, but keeps on changing from one form to another, then it helps us explain why is it that when we're heating, these two were gaining energy. It is because the electrical energy from the heater was being distributed to the water and the calorimeter, and thus facilitated this temperature rise. So mathematically, I am going to write this statement as, now this will be in another part of my experiment, which let me call it the treatment of results. Dear viewers, you will forgive me, I'm doing everything in summary because of time, and I'm very sure that my candidates out there have reference books. Some of them already have the notes, so we are just having a discussion which they can base on to go and do further reading. This is a summary of what I need from the procedure. Now I go on treatment of results. And I'm saying under the treatment of results, I'm going to conserve energy, which means that the electrical energy supplied by the heater has been gained by the liquid plus it has also been gained by the calorimeter. Let me just make this a single statement. Heat gained by the liquid plus calorimeter. Now, in this experiment, we shall pick a calorimeter which is of known specific capacity. If I'm interested in determining the specific capacity of the liquid. So I must ensure that I pick up a calorimeter which is of known specific capacity. Formula for electrical energy supplied within a certain time. If you know the current that you've supplied and the potential difference that you have caused. Those of us who have done electricity, that formula is IVT. Heat gained by the liquid, it will be the mass of the liquid, specific capacity of the liquid times the temperature change, plus heat gained by the calorimeter, mass of the calorimeter, specific capacity of the calorimeter, plus the temperature change. I forgot to mention something in the procedures that we also we pour here a known mass. I hope I mentioned that. We pour here a known mass of the liquid, and then even the calorimeter must be of known mass. Why do we need those masses? We are seeing that they are showing up below in the treatment of results. Now, if I know the value of the current, I know the value of the voltage, I know the time which I took in order to heat, I know the mass of the liquid because I poured there a known mass. I am looking for the specific capacity of the liquid under what temperature difference, under this temperature difference, because the thermometer will give me those readings. I know the mass of the calorimeter, I know the specific capacity of the calorimeter. Temperature difference caused on the calorimeter, we are saying the calorimeter and the liquid are in thermal contact, therefore it is the same temperature difference. Then I can go on and determine the specific capacity of the liquid using the mathematics, because I know this term, I know this term, I know this, I know all of this. What I don't know is only this. So if I make the specific capacity of the liquid the subject, I'm going to lead to, I think, such an equation. In fact, let me substitute this as theta 2 minus theta 1. Thermometer gave me those readings. Divided by mass of the liquid, brackets, theta 2 minus theta 1. So, because I know all of these terms, it means that I can be in position to determine the specific capacity of the liquid. Let me go through this once again, especially on the highlights. We are saying we are setting up our apparatus as shown in the figure which I've put on the board, pouring a known mass, ml, of the liquid. This you will find in the reference books of at home which you're using when you're reading through. This information you'll find. I apologize for not writing it. Then, of course, before that, I mentioned that we shall use a calorimeter of known mass, or You can even measure that mass of the calorimeter at the end of the experiment after getting these other results. Go on and measure initial reading of the thermometer, close switch, heat the liquid for a certain time, which you can compute using a stop clock if you're in the lab setting. After a certain temperature rise, a noticeable one indeed, take the reading of the ammeter, record it as I, take the reading of the voltmeter V, then open the switch, come and treat the results in this way. Why this way? We have said that the heat energy that is coming from the heater is what is being distributed to the liquid plus the calorimeter. We arrive at this as being the final expression that we can use to determine the specific capacity of the liquid. Now, when you look at my diagram, there are a few things again which I've not talked about because I wanted to pull out basically the highlights. For example, we have a stirrer. What is the purpose of this? In order for us to ensure uniform distribution of the heat provided by the electrical heater, we keep stirring that liquid so that the heat distributes itself very well. Of course, we know that liquids are not so much of good conductors. Then, out of curiosity, somebody may say that there is also a thermometer. Isn't it gaining some of this heat? It is true. It is gaining some of that heat, but we neglect how much heat will be absorbed by the thermometer. So the thermometer, we may not account for it in the treatment of the results using that equation. So, basically, what I'm saying is the electrical method for determining the specific capacity of liquids, and that can be any liquid, as much as when we're in the lab, we may restrict ourselves to using water, but it can be any liquid of your choice. These are the set of procedures which I've talked about that one needs to go through. How to present the procedures, I hope that people will go on and read in the reference books, and probably even when the teacher, when you go back to school, the teacher will give you a set of guidelines. So, this is one way. Then, I can also use the electrical method to determine the specific capacity of a solid. And if I'm to use the electrical method to determine the specific capacity of the solid, what do I need this time? This time, I'll get my specimen solid, cut it out in form of a rectangular block, a simple one. I'll drill 2 holes at a measurable distance between them, and then I'll go on and insert in one hole a thermometer, and in the other hole I put the heating element. After that, I'll lag that. Quickly, I'm going to try and draw a sketch. Ammeter must be connected in series. Those of you who have done electricity, you know that. Of course, somebody might be out there wondering, why is it that it is the voltmeter which I'm putting here and the ammeter here and not the voltmeter here, ammeter here? In the design of these instruments, in order for them to function, the voltmeter must always be connected in parallel, while the ammeter must always be connected in series with the circuit. That's another marking point. Students usually forget and then interchange the positions of those two apparatus during the presentation of their work. So, I want to What is the purpose of the lagging? I'm trying to ensure that I prevent heat losses to the surrounding by radiation in this case. Even here, I used the constant temperature bath in order to control that, that heat which could be lost to the surroundings, since in the final calculation, I do not account for it. So, this will be my setup for determining the specific capacity of a solid using the electrical method. Even in this method, I need the mass of the specimen. I need to take the temperature reading. I need to heat it up to a certain temperature change, then go through the same steps, treat the results, and then come up with the final expression. Because of time, my dear viewers, I hope that you can use the knowledge which I've provided on determining specific capacity for the liquid using the electrical method to determine the specific capacity of the solid. If not, I know through the reference books, at least if you sit down and read, you will be in position to get something. Thank you very much for being a good audience. I wish you all the best and kindly remind you to stay safe.
Twanzege Master Lutaya okuva ku Uganda Matters ICC Namugongo. Olwaleero essomo tulyongeddeyo erya hit era naddala bannaffe abali mu senior 4 ate ku ssaawa 9 paka ssaawa 10 tugenda kuba butereevu nga tugenda maaso n'enteekateeka ate ey'okubasomesa bannaffe abali mu senior ey'omukaaga ssaawa zijja kubeera 9 paka ssaawa 10 enteekateeka eyo gyeri. Era n'olunaku olw'enkya kutandika ku makya tujja kuba ne primary ate era butereevu ne senior 4 era ne senior ey'omukaaga. Essomero erya bannaffe erya Maryland High School Ntebe nkujjukiza nti gye bali era enteekateeka y'okusomesa abaana okuba nti omwana ava mu ssomero nga mulamba ajjudde bagikolako bulungi nnyo. Ennamba z'essimu 0772 osobola okubayo ate n'osobola okuba nti omwana wo atuuka ku ssomero eryo bulungi era n'aba nga afuna ebyenjigiriza ebiri ku mutindo. Tugenda kumulamu tudde ne puroguramu akalakya tova ku terefayina eyaffe.